Welcome back. Up to now, our diodes have shaped signals. This one has a completely different job, and honestly, it is one of the most useful tricks in electronics, holding a voltage perfectly steady. Picture this. Your power supply wanders. 16 volts now, a little more later, a little less after that. But the circuit you are feeding needs a rock-steady voltage that simply will not move. So here's the question. Can one cheap component act like a wall, so that no matter how hard you push, it refuses to let the voltage climb past a set value? Yes, it is the Zener diode. And the trick behind it is something we have always treated as a failure: reverse breakdown. Let us see why that failure is actually a gift. Let us recall how a normal diode behaves. You already know most of this. In the forward direction, it conducts after about 0.7 volts. In reverse, it blocks current until the reverse voltage gets so large that the diode breaks down and current suddenly rushes through. In an ordinary diode, that breakdown is destructive. It kills the part. Here is the clever bit. A Zener diode is built on purpose to break down at a precise low reverse voltage we call the Zener voltage, V sub Z, and to sit there safely as long as we do not let too much current through. Its symbol is just a diode with a bent Z-shaped bar on the cathode. That little Z is your reminder. And here is the one fact that makes everything work. Once a Zener is in breakdown, the voltage across it stays almost constant at V sub Z, no matter how much current flows. Hold on to that. It is the whole reason the Zener is useful. Let us actually see that on the current voltage curve. Current up the vertical axis, voltage across the horizontal. To the right is the forward direction. Like any diode, the Zener turns on near 0.7 volts and current shoots up. Now the interesting part. To the left, the reverse region. At first, as we go more negative, almost no current flows. The diode just blocks. But the moment we reach the Zener voltage, here at minus 10 volts, the curve bends hard and plunges almost straight down. And this is the part to really watch. Follow the operating point as the current grows. It slides far down this steep line. The current changes a lot. But look at the voltage underneath it. It barely moves. It stays pinned right around 10 volts. That near vertical wall is the entire idea. A huge range of current, but an almost fixed voltage. That is exactly what we want from a voltage reference. Here is a way to picture it. Think of a tank being filled with water. The water level is our voltage. On the side of the tank there is an overflow channel, a weir, at a fixed height. That height is the Zener voltage. While the level is below the weir, no water spills and the Zener is off. But once the level reaches the weir, any extra water simply spills over and runs away. The level cannot rise past the weir, no matter how fast we pour. The spilling water is the Zener current. The fixed level is our regulated voltage. That is exactly how a Zener holds the output steady. Now let us build a real regulator. We place a series resistor R between the input and our output node. Across the output we connect the Zener, and in parallel with it, the load resistor R sub L. The resistor controls how much water we pour in. The Zener is the weir. Now, here is the single biggest mistake people make with Zeners. They see a Zener and assume the output is always V sub Z. Do not. Sometimes the Zener is not even on. So before anything, ask one question every single time. Is the Zener actually on? Here is the test. Mentally pull the Zener out and find the open circuit voltage at the node using the voltage divider. V equals V sub I times R sub L over R plus R sub L. Then compare. If that voltage is at or above V sub Z, the Zener switches on and the output locks to V sub Z. But if it is below V sub Z, the Zener stays off. There is no spillover and the output just drifts with the load, unregulated. So test first, then trust. Keep that rule because our very first case is going to trip on it. Here is our circuit. The input is a fixed 16 volts. The series resistor R is 1 kilo ohm. The Zener voltage is 10 volts, and its maximum power rating is 30 milliwatts. Before we touch the loads, let us pull one number out of that power rating, the most current the Zener can safely take. Power is voltage times current, so current is power divided by voltage. I sub Z max equals 30 milliwatts divided by 10 volts. 30 divided by 10 is 3, and milliwatts over volts gives milliamps, so I sub Z max is 3 milliamps. Keep that in your back pocket. We will check against it at the end. Now the question. Find the load voltage, the resistor voltage, the Zener current, and the Zener power for two different loads. First, a load of 1.2 kilo ohms, then a load of 3 kilo ohms. Case A. The load is 1.2 kilo ohms. Test first like we agreed. Pull the Zener out and find the node voltage with the divider. Let us do it piece by piece. The bottom first, 1 plus 1.2 is 2.2. The top, 16 times 1.2 is 19.2. Now divide 19.2 over 2.2 is 8.73 volts. Now the all-important compare. Is 8.73 above 10? No, it is below, so the Zener never turns on. It just sits there off. And once the Zener is off, this is nothing but a plain series circuit. The input R and R sub L all in a line. The current is the input over the total resistance, 16 over 2.2 kilo ohms. Watch the unit. It is kilo ohms, so the answer lands in milliamps. 16 over 2.2 is 7.27 milliamps. The load voltage is that current times the load, 7.27 milliamps times 1.2 kilo ohms. Milliamps times kilo ohms gives volts, so that is 8.73 volts, the same node voltage exactly as it must be. The resistor takes whatever is left. 16 minus 8.73 is 7.27 volts. And the Zener? No current. So the Zener current is 0, and the Zener power 10 times 0 is 0. Look what happened. The load was heavy enough to pull the node below 10 volts, and our regulation just vanished. This is the trap. If you had blindly written output equals 10 volts, you would be wrong. Case B. Now a lighter load, 3 kilo ohms. Same test. Pull the Zener. The divider gives 16 times 3 over 1 plus 3. The bottom, 1 plus 3 is 4. The top, 16 times 3 is 48. Divide, 48 over 4 is 12 volts. Compare, is 12 above 10? Yes. So this time the Zener switches on and pins the output. The load voltage is 10 volts, locked. The resistor takes the rest. 16 minus 10 is 6 volts. Now the current through R, 6 volts over 1 kilo ohm. Kilo ohm again, so milliamps. 6 over 1 is 6 milliamps. The load pulls its own share. 10 volts over 3 kilo ohms is 3.33 milliamps. And the Zener mops up the difference. That is just Kirchhoff's current law at the node. Current in equals current out. 6 minus 3.33 is 2.67 milliamps. Notice the size, a couple of milliamps, exactly what you would expect for a small Zener. If you had gotten amps, you would know a kilo went missing. Last step, the power. V sub Z times I sub Z. 10 volts times 2.67 milliamps is 26.7 milliwatts. And always check it against the rating. 26.7 is under 30, so the Zener is safe. The output is regulated at a clean 10 volts. One caution, had that power come out above 30 milliwatts, the Zener would cook, and the fix would be a larger series resistor to throttle the current. Let us pull it together. A Zener diode is a diode built to live in reverse breakdown, where its voltage barely moves off V sub Z. That makes it a voltage reference, like a weir that fixes a water level. To use one as a regulator, never skip the test. Pull the Zener, find the divider voltage, and compare it to V sub Z. We saw both outcomes. The heavy 1.2 kilo ohm load left the Zener off and regulation collapsed. The lighter 3 kilo ohm load switched it on, locking the output at 10 volts, safely under its power limit. One line to remember: test first, then trust. Next time, we make life harder. We design a regulator that has to hold steady while both the load and the input voltage change.